Mr. Smith here. This is Algebra 2, Section 7.2, Graphing Exponential Decay Functions. So, the good news is this is exactly the same as Section 7.1, except our b value here, now we take y equals b to the x, and our b value is a value between 0 and 1. And how that modifies or transforms our graph is instead of going like this for exponential growth, we come down for exponential decay. Okay, and so last time I think I mentioned this idea of carbon dating. Right? Carbon dating. Well, it's technically exponential decay and not growth because the amount of radioactive carbon is decreasing over time. But it's still an exponential problem. And everything you're going to see in this section is exactly the same as 7.1. Again, we have an asymptote. Right? The x-axis here serves as our asymptote. Again, the idea of that is that the graph gets closer and closer and closer to the x-axis, but it never actually gets there. Okay. All right. Let's start here with this guy. So we're going to graph this function. All right, so this is an exponential decay function because this number is smaller than 1. I know it's going to be stretched by a factor of 2, which really isn't going to be a big deal to me. And then the minus sign here, that is going to reflect the graph over the x-axis. Okay, so the minus sign reflects the graph over the x-axis. So what should have been an exponential decay function up here, coming down towards the x-axis, is now going to reflect over to the x-axis down onto the bottom half of the graph. And so it's going to look something like that, right? So I'll just roughly give me a graph like that, okay, for just right now. And now to get an exact idea, I'll use an XY table. I'll pick a couple x values, a couple y values, and we'll go from there. So 3/4, let's go to the 0th power. It's just 1 times negative 2 is negative 2. 0, negative 2 is there. I plug in 1, 3/4 to the first power is 3/4 times negative 2 is negative 6/4. That's that. If I go to the second power, 3/4 squared is 9/16. 9/16. And that times negative 2 is negative 18/16. Cubed. 3/4 to the third power is 27/64. But now times negative 2 is negative 54/64. And so we see this graph. Does something like that. Again, when we want to talk about domain and range, the domain of these functions is all real numbers. And the range, in this case, if I start down here at negative infinity, well, the graph is going to be down there with me, right? So at negative infinity, the graph is there. And as I come up the y-axis, the graph is still there, this is still there, until I get to the x-axis, and the graph is no longer there. So the range is from negative infinity to 0, not including 0. Okay, the range is the y values. And so we look on the y-axis, and I start down here as low as I can go. And I say, well, is the graph down there with me? Yes, it is. It has an arrow. As I keep coming up, I look and I say, is the graph with me? Is the graph still with me? Is the graph still with me? And right here, the graph is still with me. But as I get to the x-axis, it no longer is. So we don't want to include 0. And certainly, we don't want to be talking about values up here. The graph isn't up there. Okay? Here's Here's another graphing problem. Why don't you guys try this one? All right, so when we look at this, we should see a vertical shift up 1 unit, and this is going to move the asymptote as well. A horizontal shift 1 unit to the right. Since this number is 3/5, this is going to be an exponential decay function. Exponential decay, and we have a stretch factor here of 2. I made a quick XY table to an 11/5, so that's like this guy there, and 1/18/25, so maybe something like that. Okay. If you wanted, you could pick a few more x values, get a few more y values to see. But roughly, this graph is going to shift like this. Okay. Again, the domain of these functions is all real numbers. And the range in this case, if I start at -infinity, the graph is not down here, not down here, not down here, not down here. When I get to 1, the graph is still not there, but as soon as I take 1, the smallest step I can possibly conceive of, and I step up, now the graph is there. So 1 to infinity is the range. Okay. And again, if you look at the vertical shift, that will generally tell you where the asymptote just moved to. Okay. One other way here that we could write the range is we can say y is a real number. Y is a real number such that y is strictly greater than 1. So these would be the two ways that you could write this idea. All right. So the first half of this section is on the graphing piece, and the second half looks at some applied problems. Now, before you get too worried about having to learn another formula, you should recognize this one. It's exactly the same that we saw in section 7.1, except instead of adding here, we're now subtracting. Right? A is still our starting value. R is still our rate expressed as a decimal, and T is still the amount of time in whatever unit we're talking about, years, months, minutes. Okay. All right. So here we have a snowmobile that costs $4,200 and the value depreciates by 10% each year. So again, the formula, 1 minus r to the 10th power. Okay. So write a model given the value and everything else. So y equals 4,200, 1 minus 0.1 all to the 10th power. One minus 0.1 is just 0.9, so we could just think of it like that. Okay. In the second question, they ask us to calculate the value after 3 years. We just use our graphing calculators or any calculator to get that piece. And if we do, I think we get the value something like 3,061 point something. And lastly, they ask us to find how many years is it going to take for the snowmobile to be at a value of $2,500. So what I would tell you to do is graph this, y equals 4,200.9 to the x power, and also graph y equals $2,500. So you're going to graph both of these pieces and look for the intersection point. Graph both of those pieces and look for the intersection point. Now, of course, you're going to have to zoom out because these values are going to be very big. So you want to make sure that you zoom out. And probably the easiest way to do it is start with zoom standard. So usually that's zoom number 6, zoom standard, and then change it to zoom fit. And that should work on almost all the calculators represented in this room. Okay. So once you have the zoom right, then you can hit second calc intersect, or you can use the Inspire's intersect option to find out how many years this should take. And it should be x should equal 4.92 years.